Yeah, so welcome. How many of you have been to KubeCon before? So 3 people. How many of you have seen Cueflow before? I've seen a few. How many of you have actually used it? Just getting a sense of the audience. Oh, like 4. So yeah, this is a good place to be if you haven't used Kubeflow before. How many of you have used Tensorflow before? Most of the audience. OK. Great. So today we're going to talk about bringing your data pipeline into the age of machine learning. My name is Gaun. I am a product marketing manager at Mesosphere. I've been in the Kubernetes community a very long time. I'm a CNCF ambassador, if you're interested in what that program is. If you've seen that machine walking around with that face on it, you could ask that device, and they could tell you what a CNCF ambassador is. But basically, we advocate for CNCF technologies like Kubernetes and Core DNS and the rest of them that we learned about in this conference. Previous to that, I was an analyst at Gartner. I covered public cloud, particularly public infrastructure as a service. You can follow me on Twitter. This is not my first KubeCon speech. Yeah, so I've been here before. I've done keynote speeches at KubeCon. I've also traveled throughout the United States and Europe teaching people about Kubernetes for the past 3 years.
I'm Jörg, so I'm a technical community lead. What does that mean? That I'm basically picking up community projects and make sure that they work well with Apache Mesos and then DCOS. So when we start out new projects like Tensorflow, like Cueflow, they often end up with me, and then I work with the community of getting that going. Originally been a co-developer of Apache Mesos, but yeah, more recently I really enjoy this machine learning area, data science in general. So I believe this is why it's a good fit to co-present with Chris here. And yeah, so most hands actually went up when we asked like who knows TensorFlow. But maybe just to recap, kind of the idea why deep learning right now is becoming so popular. First of all, we got more compute power and we got more data, and that actually means that this traditional machine learning pipeline. Imagine we want to have this classifier dog or cat or hot dog, non-hot dog. What happened in traditional machine learning? We had a very smart, highly paid person sitting there, and he would extract features. And with his features, and could build like an SVM or some kind of classification mechanism to actually classify those images. And then we had our output: hot dog, non-hot dog, dog, cat. With machine learning, this actually requires this extra effort, and with deep learning, we're replacing this human basically with data and more machinery. So instead of having someone who also might have a bias in deciding what kind of features he might want to extract, we actually just leave that up to the machine, because if we have enough data, we are much better in figuring it out from the data what are the best features to actually decide this dog, non-dog question here. So how does it typically look like? We got like some labeled pictures where a pure human draw like some boxes around this dog here. So labeled input data, and the more of this input data we have, the better. And then we come up with like a basic network structure, and we start training the weights. And then we have a trained model, and then the second step comes, and this is actually the inference step or the serving step. And then we have our model, and we deploy it to production. So we're actually getting new, previously unseen images, and then we serve them. And already in this slide, this is something when I look at conferences or when I look at blog posts, a lot of people focus on like the first site training. What are the best images? What is like the best models to use? How do I train best? And how do I optimize my hyperparameters? And that's all very important. But like in production use cases, the second step of how do I serve this model, how do I actually build this into a complete pipeline is at least equally important. Tensorflow, almost all hands went up, so I don't want to say too much, but it's basically a library often used to build deep learning models. It's not only deep learning models, actually it can also do more traditional machine learning. And the nice part about it is that we kind of have an abstraction. We have multiple high-level interfaces on top, but in the end we are coming up with like our model, and then TensorFlow can actually distribute that across different infrastructures, so it can optimize my learning process for a setup where I have GPUs, where I have CPUs, when I'm distributed, when I'm non-distributed. So I, as a data scientist writing my model, I don't have to worry about it if I use the right APIs, And just if we look back how TensorFlow has been trending on Github Stars. So here, this first, when it jumps up, this was actually when Google put TensorFlow on GitHub. And you can see it steadily increasing. And it's really an impressive growth. I was just at TensorFlow Developer Summit last month in Mountain View. And it's really impressive. This was like the largest conference. I've always felt Kubecon is large or is getting much larger. But that was really impressive for such a young project to see such a big conference coming up there. And you can also see, like, if we take Github Stars as kind of a metric, how it compares to other projects. For me, honestly, there are really good other projects as well, but it simply shows that there's a lot of developer power and also a lot of users in the TensorFlow realm. TensorFlow, how does that look like if I do that as a single developer? Being a single developer, and this is what I actually really like about it, I simply download the libraries and I can run that on my own machine, and within, if I download a pre-trained model, I can actually get that working with like an hour time, and I've trained my first model. So it actually makes it very simple being a single node developer just testing things out. But if we actually turn over and we leave our own desk where it's simple, but then we actually want to put that in production, it becomes a bit harder because all the problems which are like non-existent on my laptop, we have when we want to do that in production. So we have to consider, where do I store my data? If we want to do machine learning, deep learning right, we need data sets which don't fit on a single machine. So I need some kind of distributed data storage. I need to prepare data. Typically, data sets I get from anywhere in my production cluster. In very rare cases, I might use them directly, but often I have to prepare, cleanse them, which we'll see in a second. Then the data scientist work starts. I actually have to explore the data. And once I have a kind of idea what I want to train, I need to kick off like a large job utilizing a large cluster. My data set is large. And even in a distributed setup, this can take days. And while this is running, it's really important to keep monitoring in mind. TensorBoard is really nice to monitor kind of the training progress. But distributed infrastructure, it already kind of points it out. I also want some monitoring for this overall infrastructure. Then also debugging, tf-debug, it's nice. How many of you have seen that it's actually, there's an alpha or beta version included in TensorBoard in the latest version? So previously, like tf-debug used to be this command line thing, which it was helpful, but it was kind of annoying to use. And in the latest version, they actually put that into TensorBoard as well. So that's a great step for debugging forward. And then the last part, and as mentioned earlier, also one of the important parts, actually model serving is when I put this model into production. And there are a bunch of challenges there, like how do I get my data in there, like how do I trigger requests, how do I choose which model I want to serve? I kind of need 0 downtime deployments for my model serving after all, as this training process is not a one-time thing, it's actually an iterative thing when I get more data, when I refine my models. So also the model serving side kind of has to reflect that. All right, so with that, the typical workflow, if I want to run TensorFlow on a distributed setup, or just the training part, it becomes more complex. So I have to pick a bunch of machines, I have to install TensorFlow on them, and if I'm not using the right APIs, I have to adapt my code to that. I would actually just encourage everyone, stick to those newer high-level APIs, because they'll automatically be able to distribute your code. They'll be automatically, they can utilize also TPUs if you're running on Google infrastructure. So it kind of abstracts away from where I have to write my own entire cluster setup. But even in that scenario, I still have to specify the cluster spec, with those IP addresses for my distributed setup. And then I have to deploy my Python code, or however I wrote it, onto all files, and then I can finally kick off the training. And also, like down here in this node setup, there are different types of nodes. I might have worker nodes, I might have parameter servers. So it's a kind of art of how to set that up efficiently that I get the best output of my cluster. So, and a distributed job running for days, what do we expect? They're going to be failures. And that can be, depending on the failure type, this can be rather annoying, as if I have my hard-coded cluster spec with all those IP addresses, I might actually have to restart that job simply because nodes have gone down, and if half the nodes are down, my performance is going to be pretty bad. This is actually, these failures, this is actually true for any distributed system. And you should keep that in mind with also the other big data tools we'll be talking about here. With that, I would actually hand back to Chris, actually, who's going to talk about the entire pipeline from start to end.
Yeah, so if you haven't seen or guessed by now, we really want to not only get you up and running on Kubernetes, but get you workloads running on Kubernetes. And a great workload to run on Kubernetes is Tensorflow. And there's great tools out there, including something that we'll investigate called Cueflow. But we want to, all the other sessions I've seen on Cueflow or Tensorflow on Kubernetes, they often had some magic behind it. And it's some of these external parts that you would have that might be part of a public cloud or something. So I just wanted to go through the entire pipeline so that you could be successful in setting up from your database all the way to your model serving. So in a typical deep learning pipeline, you have your data and streaming. This is where you're housing your data. It could be in the public cloud, or it could be in an open source tool. There's several ones that we'll cover today that are extremely popular. And then you have your users. So in one of the tools that we'll investigate, some of this is given for you, but there's other users preparation type software that you could use. There's also Spark, which we saw today during the keynote. And that's a good way to do data preparation, and we'll have a live demo of that as well, some data preparation that we're doing before we ingest it into TensorFlow. And then we have the frameworks and the cluster. So the cluster is obviously Kubernetes that it's landing on, and there's many different deep learning frameworks out there. And then the models and the model serving. So in Kubernetes world, there is a tool called Kubeflow. A few of your hands went up. You've used this before. This allows you to get Kubernetes up and running very easily. TensorFlow up and running very easily on Kubernetes. So what does it include? It automates the distribution of deep learning. And so it installs TensorFlow on Kubernetes. With that, it also includes Jupyter Notebooks. It currently works only on Kubernetes. If you have other distributed systems, it won't work on that, but it's open for commits. And then it requires, to get it set up, requires some knowledge of KSonnet. It is a tool for packaging and deploying to Kubernetes. So I'm a marketing guy, and I was able to use it in a day and figure it out. So I'm sure the technical audience will have no problem. So that will get you TensorFlow on Kubernetes. So what is the stuff that I've seen that I've said has been magic when I've seen this demoed before? It's often the data part of this. So connecting your data is obviously one of the most crucial pieces for analyzing any data that you're going to do. There's open source tools that are available that you could store and stream your data: Spark, Kafka, MongoDB. We'll do a Flink demo today. And then a lot of the demos I've seen use managed options in public cloud as well, Google Cloud Storage or something of the like from the other vendors. So in the data pipeline, you saw a few steps. One the first step is input data management. So what are the problems there? As Jörg was saying, you have a large amounts of data. The availability of the clusters, oftentimes you have a fire hose of data coming in. More data is coming in all the time. The solution are these open source tools or some public cloud options that are available, like HDFS, Kafka for streaming, Cassandra for distributed databases. So these are all, I would say, in the big data market, which has been growing since its first inception in, I would say, mid-2008, 2007 type time frame. And why have they been growing? Because we're creating more and more data every day. There's also large and existing data streams that we need to connect to. So this is a lot of times you want to use something that you're familiar with when you're working with TensorFlow. You've already used HDFS or you've already used Kafka, and you might not necessarily want to go to one of the public cloud APIs and their proprietary tools. Also, there's often strict data governance around, especially in European companies. I was actually talking to a European company the other day at Kubecon, and as soon as they analyze the data with their deep learning tool, they actually have to erase it, and that's because the government actually doesn't allow them to keep around the results because it is customer data. So data preparation. So if you're doing a demo data set, it's almost like a hello world. It's very easy to do, but that's the exception to the rule. Oftentimes you have to do a lot of data cleanup. The timestamps might be off, or you might be collecting it at different frequencies, so you have to match it up. There's obviously oftentimes a lot of junk in data. We've all seen it. All of us have that have worked with data before. So you need to have tools in order to clean that up, so do some analysis. We'll cover Spark and Flink today. I believe our demo specifically is on Flink. So we'll see doing some of that in our demo. And then model management. So the ability not just to create the models, but actually distribute them and actually get them out to your clients. And so there's several open source tools for that as well. We already covered HDFS. MongoDB is another one. And this is something that we will demo as well. So that's your deep learning pipeline. Again, you have your data and streaming, your users, your frameworks, and your models and model serving. And what Cueflow is doing is helping you with your users, your models, your model serving, and obviously getting TensorFlow working on Kubernetes. So today we'll actually be using, and you can use public cloud to get the data obviously as well. We'll be using Mesos to get some of these open source frameworks that we talked about, like Flink and HDFS. Mesos has a long history of working with these big data frameworks in very large environments, thousands of nodes and mission critical type organizations. And so what Mesos does is it almost treats your infrastructure like Kubernetes treats pods. So you could say, I want this amount of infrastructure, and it gets it up and running. And then if some of the infrastructure goes down, it actually, in a declarative model, checks, oh, the desired state does not match the reality of the state of what I want. I don't have enough Kubernetes worker nodes, for instance. And it could easily replicate and spin up another Kubernetes worker node. And so there's a lot of container management solutions that work on Mesos. Kubernetes is one of them. Marathon's another. There's one that has been released 2 weeks ago by by Netflix called Titus. And they actually use Mesos to spin up 200,000 clusters of Titus per day. I have no idea why they need 200,000 orchestration clusters per day, but that's what they said that they do. So with the Mesos architecture, the way that it works is that we have an agent on each one of these nodes, and they're offering resources to all these different schedulers who have their own way of doing things. So Kubernetes scheduler is scheduling pods in one way, then the Spark scheduler is doing it in another, and then Kafka is doing it in another. So they're asking for resources, and the Mesos scheduler says, oh, okay, Kubernetes needs 6 worker nodes, so it gives it the amount of CPU and memory that it needs. And with that, move to the demo.
Cool. can I just maybe add like one more sentence here? So as you mentioned, like Mesos is treating all those systems like Kubernetes is treating your pods. So this is why it says like two-level scheduling. So Mesos is kind of the resource scheduling. Mesos only cares about resources, but then the way in which different systems like Kubernetes, like HDFS need to treat tasks. This is actually a second level, and this is very application specific. So as you mentioned, HDFS needs a totally different treatment, and this is first of all when deploying it, but more importantly when there are actually failure scenarios. If a pod Nginx pod fails, I'll simply reschedule that, and I don't necessarily care where. But if my HDFS data node is failing, or if both my HDFS name nodes are gone, I actually need a more complex recovery step. And so this is kind of what those schedulers, if you want to compare them to operators, like operators for distributed systems, are pretty good at. All right, we see demo. So when being on the cloud, and this is actually where Cueflow, I really like it, is when I'm running, for example, on Google infrastructure. So when running on Google infrastructure, I have actually managed Spark I can use for data cleansing, data preparation. And so that might read from cloud storage, it will read my data, and it will just might write it back into the cloud storage here. Then I can use my typical Kubeflow workflow. So I'll spin up a Jupyter notebook. I then explore my data. I will train my model using TensorFlow. I can use TensorBoard to actually monitor the progress. I can use TF-debug, 2D debugging. And then you've got like two options in Kueflow itself for serving. So I then can serve my models. And so once I have my model serving up there, I actually need a way of hitting it with requests. So there are also different streaming solutions in those cloud settings. Now the question is just what happens if I'm not in one of those cloud settings? What can I do? So if we are open source, and also if we want to be independent of those cloud tools, the typical solutions I see out there are Spark for data cleansing. So Spark, I typically see that if I have like batch workloads. So if I already have my data stored in HDFS, and then I just flow through it. And HDFS, it's a very scalable storage. And then for streaming, Kafka is a very good solution for actually streaming the request and then hitting my TensorFlow serving. There's actually something, has anyone heard of the rendezvous architecture? Yeah. So this is actually by Ted Dunning from Mapper. And this is actually heavily relying on Kafka, both for hitting different serving endpoints. So the question is, what do I do if I have different models and I don't actually know which one gives me the best result? Because this training process, as mentioned, it's iteratively. So I end up with like many hundreds of models, and I then need to pick which ones are best. So the idea is kind of to take multiple models at the same time, have a Kafka stream serving the request, and another Kafka stream actually collecting the results, and then I decide which of those results I want to use. So this down here, this is basically Kubeflow, and it's very powerful and very helpful. And everything on top, this is then up to you what you want to use depending on your infrastructure. If you are in AWS, you can use the AWS tools. If you're in Google, you can use the Google tools. If you're on-prem, you need to come up with alternative solutions. So this is kind of the open source version of this, which might even, if you consider, even though you're running in the cloud, it might be a good choice simply because you're not tied to a particular cloud vendor. And yeah, this brings us to the demo. And for this demo, as said, there are many, many options, but as we are working on Mesos and DCOS, we kind of choose that for that. So how much time do I have left? 5 minutes with questions, okay. So here, we have a cluster where like all those tools are running on AWS in this case, but this can also be an on-prem. So I actually have a system where I have Kubernetes running. This is pure Kubernetes, and if we look at that, I already deployed Kueflow on it, as it takes a while. It's in another namespace. but this is just the open source Kubernetes Cueflow. So here I can see this is my default, very simple, it's the getting started guide Cueflow example, which I deployed here. And it's not so bad with case on it. And then we have HDFS, which is holding some of our input data. We have Kafka for streaming, Flink for also data cleansing. So let me just switch back to the slides for 1 second. So if you recall this picture here, Spark is really great if I have like a batch processing. So if I have my data on HDFS and then I run a batch job, I cleanse it and prepare it for my workflow. But often I even have like a stream of data coming in. So if I have this event stream coming in and then I want to store this data, what I also seen people do is they really use like a streaming system. Spark could do that as well, but Flink is my personal favorite there, but personal choice. So they actually use Flink and they pre-process the data and then they actually write it into HDFS here. Okay. So having that said, what I would do now, I would actually just deploy a Spark job to cleanse my data. So it will read from HDFS and write back to HDFS. And I have my cheat sheet here. So I'll explain that in a second. Didn't you install the Spark CLI?
No, I did not.
All right, then I just need to do that on the fly. Sorry, it just takes 1 second. I asked him before.
Oh, I installed the Kubernetes CLI though.
So it's just a CLI extension for kind of the kubectl for DCOS for Mesos. And this is installing right now. And here we can now submit a Spark job. It's only as long as I used a gist to store it, as I didn't want to create a full domain for that. So okay, we submitted our job. So if we now have a look at the Spark UI, we should be able to see that hopefully our data cleansing job has been running successfully. So it's still launching. So those of you who know how Spark works, it's launching our driver here and still processing our data. But we'll just leave that open and continue with our demo so far. Next step is we want to access the default Cueflow. And for that, it's our nice port forwarding. I think I only need this. Good. And here we come up with like our Jupyter Hub. How many of you know Jupyter Hub? So Jupyter Notebooks, as Chris mentioned earlier, they are like a great way for data scientists to kind of explore their data sets. I mean, if I'm a data scientist, I want like an easy to use interface. And Jupyter Hub is a way of easily spawning those Jupyter Notebooks. And here we go. And so I already spawned one. Like spawning a Jupyter notebook, it's a huge Docker image. I think it's like a 10 gigabyte Docker image, so it takes a while. So this is why I actually launched one up front. But we can easily launch, if I log in with another user from Jupyter Hub, you can launch as many as you would like. So in here, I want a new Python 3 context. Great, so this is what Jupyter is about. I simply get this easy shell, and there I can now execute a Tensorflow program, basically. And I have one here. So this is the default MNIST example, and what it does, it actually downloads the data set from the internet. It's like the default TensorFlow one, but we'll change that in a second, or depending on how much time there's left, 5 minutes with questions. We can easily change that to also move it somewhere else. And so executing this now. So it takes a while to run. And yeah, those warnings are because the example, but it's the official example. I wanted to stick to the official Cueflow example. It's using deprecated UIs, but don't be alarmed by this. It's just deprecation warnings. And one thing why I personally, we've been talking about TensorFlow quite a lot, but actually there are other tools which makes this easier. So one thing which is a little annoying for me with TensorFlow up until very recently is like the session.run. So what TensorFlow does, I built a very static compute graph, and then I run this compute graph over and over again. In the 1.7 version, they introduced eager execution. And other tools, for example, PyTorch, I really like that as a feature of PyTorch. They actually allow me to do that on the fly. So I can actually get my define my entire graph on the fly, which means I can also output after each step, and I can debug after each step. And yeah, it ran. We have an okay-ish, for this number of iterations, output accuracy. And now, this takes a bit longer. So now I can basically switch in my HDFS backend. And this is very important for TensorFlow for multiple reasons. So there are actually 3 spots in this program why I might want to have that. And first of all, it's for import. So what we do here, this is a very small data set which has been downloaded into the Docker image running Jupyter here. But if I'm going at more scale, I probably want to read it from HDFS in my cluster. The second thing is then the model which I output and I write somewhere. And the third thing, and most important probably, or others are also important, but also very important thing is the metadata. So how many of you have used TensorBoard? So TensorBoard, it needs somewhere from where to read those checkpoint files. And there HDFS is a great option. So just when I need some kind of distributed file system where while this job is running, it can actually write those metadata checkpoints, and then from where TensorBoard can read them, and later on also other tools can read this metadata to visualize that. As we only have 2 minutes left, I would actually go over to questions. I'll be around, and I'm happy. So the next step is basically we export that to HDFS. We look at HDFS where it's stored, and we use the data we previously cleansed with a Spark job.
Yeah, and the slides will be online if you look under the talk. I believe they're there. And all the steps are in there. Everything that you saw is open source. So if you want to go and do it yourself, we could probably put these commands in there. We don't have them right now, but that should be simple to do. I'll put them in the deck after I'm done. So are there any questions on getting TensorFlow up and running and Kubernetes, any of the open source tools that we saw? Yes?
Right now, you need to use the Jupyter notebook, or tell that if you are married with and want to use it directly from out without the Jupyter notebook, that you don't like notebooks.
Yeah.
Don't do notes about that? Is it possible? Is it easy?
Yeah.
Yeah, so we stick with Jupyter for today because that's what you get from, yeah, okay. Yeah, just make that question.
So for production, or the workflow I typically see is you go in, your data scientists actually train that, they explore. So Jupyter for me, it's more of like for exploring data and getting a feel for the model. But once you have then a production scenario, you should also have this definition, this Python file. This should be somewhere versioned in GitHub or whatever Artifactory version storage you have. And then you're actually firing off that job against the cluster. So also this example, you can get, there are tricks in which you can get Jupyter against a distributed cluster. In this scenario, it's actually just using the resources inside the container. You can't connect it against an external cluster. But like for the large-scale learning, you want more. So if you go back to this pipeline, like this user is just like the initial analytics, but then once we're at the framework and cluster level, you wouldn't, typically you wouldn't launch that from Jupyter directly.
Yeah, so that's the last question I think we'll take, and then, sorry, we're just out of time, I think, but we'll be up here, and then we could take questions up here. And we'll be around for the next 10 minutes, and then if we go over, we'll go into the hallway and take questions out there. Right, I think we're out of time, right?
Yeah.
All right, thank you.